Let me take you on a journey. I want to start with a very simple concept and explore it in a way that will give you an appreciation, a glimpsing insight into how one central branch of higher mathematics works. We'll start by looking at a shape you've seen too many times to count, but look at it perhaps in a way you've never done before. It will be our first stepping stone to meeting an incredible number. This beautiful brute. It's the size of the equally incredibly named monster group. I don't think it gets much cooler than this. Let's go. The monster group is one of the most amazing objects ever discovered in mathematics. To understand it, we have to enter the world of group theory. Groups are things that arise when we look at symmetry. Take a triangle with equal sides and label its corners 1, 2, and 3. Notice that we can rotate the triangle clockwise 120, 240, or 360 degrees around its center, or reflect it through its axes A, B, or C, and we get the same shape. While the corners and sides have changed position, the overall triangle is still in the same position as it started. That's not the case if we rotate the triangle through 90 degrees or reflect it vertically through its center. So these 6 moves preserve the symmetry of the triangle. Let's call the rotations R1, R2, and R3. But let's also rename R3 as 1 because a 360-degree rotation has the same effect as not rotating at all, which is like just multiplying the triangle by 1. Let's also name a reflection through the relevant dotted line by the dotted line itself, that is A, B, or C. Now play around with combinations of these rotations and reflections and you'll realize that doing any of these in any order just gives us one of the 6 symmetry moves. For example, an R1 followed by an A has the same result as just doing B. The sets R equals 1, R1, and R2, and the set S comprising 1 and A are called closed because if you do a combination of things in that set to the triangle, you just get another thing in that set. For example, doing R1, then R2, then R2 is the same as just doing R2. Or doing 1, then A, then A, then 1, then A is just the same as doing A. So the full group of 6 symmetries, 1, R1, R2, A, B, and C, can all be reached by doing one thing in R and one thing in S. So we can write G equals RS. Let's have a closer look at the groups R and S. They're really important here. R is actually known as the cyclic group Z3 because as you rotate the triangle, the corners cycle around. 1 goes to 2, 2 goes to 3, 3 goes to 1. S is known as the alternating group A3. And you can see this because when we apply reflection A, corner 1 stays in position while corners 2 and 3 alternate. Similarly, applying B alternates 1 and 3, and applying C alternates 1 and 2. These sorts of groups, cyclic groups and alternating groups, occur all over the place in this branch of mathematics called group theory. Now, it turns out that while the group G can be written as G equals RS, we can't break down R or S any further. We can't express them as the interaction of any smaller groups. Because R and S can't be broken down any further, we call R and S simple groups. To give an analogy, and I must stress it's a loose analogy, in the same way that the numbers 2 and 3 are prime numbers and can't be broken down into smaller factors, and these prime numbers 2 and 3 multiply to give us 2 times 3 equals 6, the simple groups R and S combine to give us the group G. Now, when I say loose analogy, you might notice I'm treading pretty carefully here. That's because the mathematicians who work in this area have some very strict definitions about the way R and S combine to give us the group G. And when we get further into group theory and study objects more complicated than triangles, the analogy with prime numbers as factors of bigger numbers doesn't really hold up all that well. It's not important for what we are considering today, but please understand why my language might be a bit fuzzy here. The last thing I want is a group of angry group theorists on my case. Those guys and girls play for keeps. All you need to know is that often big, complicated groups come about from the interaction of smaller groups. And some smaller groups can't be broken down any further. They are sort of building blocks of the more complicated groups. The cool maths name for this particular group we're looking at here, G, is D3, or the dihedral group D3. So earlier, when we wrote G equals RS to capture the symmetries of an equilateral triangle arising from the combination of rotations and reflections, the way a mathematician would write this is D3 equals Z3A3. I should point out, most maths nerds don't see this sort of stuff until second year university. So if you've understood it so far, give yourself a massive high five. If you haven't quite got it all, take a breath and go back over the video so far until it sinks in. I back you to get this. Now let's extend this approach to another common shape. It won't surprise you to know that different shapes have different symmetries. It's not hard to work out the corresponding set G if we started with a square. Why don't you take a moment, draw a square and play with the symmetries. Like the triangle, you should get an interesting combination of rotations and reflections. Playing with these symmetries gives us the dihedral group D4. And again, we can see that D4 can be thought of as coming about from the combination of an appropriate cyclic and alternating group. In fact, it should be obvious that as we move up through 5-sided shapes, 6-sided, 7-sided, and so on, we keep getting dihedral groups. So because there's strictly no limit on how many equal sides there can be on the polygon we choose, we could use a triangle, a square, a pentagon, hexagon, an 18-sided octadecagon. Yes, that's what we call it. Because they can get as big as we want, up through thousands and thousands of sided objects and beyond, this means there are an infinite number of dihedral groups. But they are all dihedral groups. There are also an infinite number of cyclic and alternating groups playing the same role as Z3 and A3 did in the example of the triangle. But they are essentially the same sorts of groups. For over a century, mathematicians known as group theorists have wanted to know all the types of symmetries that are out there and the types of simple groups that there were. So they moved on to studying more complicated objects than geometric shapes like triangles and squares. They examined all manner of sexy looking things like matrices and vector spaces. Now, it doesn't matter that both of those things might make you feel a bit queasy. All you need to understand is that they examined these objects through the same lens that we've looked at the triangle and the square. They asked, what can I do to an object like this that preserves its symmetry? And once I've looked at the group of actions that preserve symmetry, what are the simple groups that play a role in making up this larger group? In the same way that a few minutes ago, we found that Z3 and A3 combined to give us D3. And Z3 and A3 can't be broken down into any simpler groups. As the mathematicians looked at more and more elaborate objects, they found more and more elaborate simple groups. What they wanted to know was how many different types of simple finite groups are there? Is there an infinite list, or are there only a given number of possible simple groups? It took decades, even you could argue centuries of work by over 100 great mathematicians to eventually conclude that there are 44 types of simple finite groups, and that all finite groups are generated by a combination of these simple, fundamental building blocks. The entire exercise is thought by many people to be one of the great achievements in the history of human thought. The list of finite simple groups features some, like the alternating and cyclic groups we met earlier, that can get as large as we want. For example, as we mentioned, by extending the shape involved from triangle through square and beyond, we can make a cyclic group as large as we want. But the collection also features a list of groups called the sporadic groups that only occur once and have a set, finite order. And on any such list of simple groups, well, one dude has to be the biggest. There is indeed a biggest sporadic group, and it doesn't disappoint. Eventually, in the early 1980s, they found one absolute giant called, fittingly, the monster. Now, the group G that we looked at above had 6 elements, so we say it is of order 6. It's a mathematical object that describes the 6 symmetries of an equilateral triangle which lives in 2 dimensions. It was generated by 2 simple groups of order 2 and 3, respectively. So would you like to know the order of the monster group? Well, strap yourselves in for the ride. The monster contains an incredible, brutal, 54-digit long number of symmetries and belongs to a mathematical structure in 196,883 dimensions. Don't worry, I've got no idea what it looks like either. But the thing that in the same way you can see the cyclic group of degree 3 as generating the symmetries of an equilateral triangle in 3 dimensions, there's another simple group out there in 196,883 dimensions. That's just gorgeous if you ask me. It's a monster, but a beautiful monster nonetheless.